Watch this metal rod. One end is hot, the other cold. And as time passes, heat flows until the temperature evens out. You've seen this 1,000 times. Coffee cooling. A pan heating. A room warming up. Now, here's the question that launches one of the most powerful ideas in all of mathematics. Can we predict the temperature at every point of this rod, at every moment in time? Notice what makes this hard. The temperature isn't just one number changing in time. It's a number that depends on where you look, and when you look. Two independent variables. And the moment a quantity depends on more than one variable, ordinary calculus isn't enough. The tool we need is called a partial differential equation. By the end of this video, you'll know what that means, how to read one like a sentence, and two fundamentally different ways to solve one. Let's begin. Let's start with something familiar. If I only care about the average temperature of my coffee, that's one function of one variable. Temperature as a function of time. Newton's law of cooling tells us its rate of change is proportional to how far it is from room temperature. That's an ordinary differential equation. An ODE. One independent variable, so there is only one kind of derivative. dt by dt. The word ordinary literally means derivatives with respect to a single variable. But our rod is richer. Temperature depends on position x and time t. So t is a surface. A landscape sitting over the xt plane. And on a landscape, slope is no longer one number. Standing at any point, I can ask, how steeply does temperature change if I walk in the x direction, holding time frozen? Or, how fast does it change in time, staying at the same spot? Each of those questions defines a partial derivative. Written with this curly symbol, to remind us that we're only varying one variable, and deliberately holding the others fixed. So here is the whole definition, and it's less scary than the name. A partial differential equation is any equation that relates a function of several variables to its partial derivatives. That's it. The difficulty of PDEs is not in the definition. It's in what they can do. Here is the equation that governs our rod. The heat equation. Most students meet this as a formula to memorize. Let's instead read it as a sentence, because every PDE is a sentence about how nature behaves. The left side asks, at some point in the rod, how fast is the temperature rising or falling, right now? The right side is where the meaning lives. That second derivative with respect to x measures the curvature of the temperature profile. How the value at a point compares with the values right next to it. So let's zoom into that right-hand side, and see what curvature actually says, one point at a time. Look at one point, and its immediate neighbors. Take the two values next door, and mark their average. This point is colder than the average of its neighbors. The curve bends upward there. Positive curvature. So heat flows in, and its temperature rises. In fact, there are only three things a point can be doing. Colder than its neighbors, the curve bends up, and it heats. Hotter than its neighbors, the curve bends down, and it cools. And if it sits exactly on the line between its neighbors, nothing changes at all. So the heat equation, read aloud, says, every point in the rod is constantly trying to become the average of its neighbors. Remember this sentence. It is the entire heat equation, and later in this video, it will become our numerical method too. And the rate of that homogenizing is set by alpha, the thermal diffusivity. A single number that encodes the material. Same initial spike of heat. Copper relaxes fast. Brick relaxes slowly. One number, alpha, and the whole personality of the material is in it. This is the mindset shift I want you to take away. A PDE is a local rule. It never says what the whole solution looks like. It only says what each point must do, based on its immediate surroundings, at each instant. The global behavior, the smooth elegant relaxation you saw in the opening, emerges from billions of points obeying one tiny local rule, simultaneously. Nature computes locally, everywhere, all at once. Once you can read one PDE this way, you can read them all. Let me show you 3 more sentences nature wrote. Once you can read one PDE, you can read them all. Let me show you 3 more sentences nature wrote. The wave equation. A plucked string. Same curvature term on the right. But now it drives acceleration, not velocity. A point displaced above its neighbors doesn't drift back. It's pulled back and overshoots. Curvature acting on acceleration gives oscillation. Waves. One symbol changed. The physics is transformed. Laplace's equation. A heated plate at steady state. 0 on the left. Nothing changes in time anymore. This equation says, every interior point has finished becoming the average of its neighbors. It describes equilibrium. Steady heat flow. Electrostatics. Groundwater seepage. The same equation, each time. And Navier-Stokes. The momentum equation of every fluid you've ever seen. I keep it on screen just long enough to be honest about it. This is a PDE too. Just with more terms, in more variables, and nonlinear. And whether its solutions always behave is literally a $1 million open problem. Notice the pattern across all 3. Time derivatives on one side. Spatial structure on the other. And a physical constant negotiating between them. Learn to read that grammar, and no PDE will ever look like random symbols again. So how do we actually solve one? Let's take our rod, hold both ends at 0 degrees, start with some arbitrary temperature profile, and predict its entire future. The classical strategy is called separation of variables, and it starts with what looks like a reckless guess. What if the solution is a product of 2 simpler functions? One depending only on position. One depending only on time. Why guess that? Because of what happens when we substitute it into the heat equation. The time derivative only touches g. The space derivatives only touch x. Divide through, and something remarkable occurs. The left side depends only on time. The right side depends only on position. But they're equal. For every x, and every t. A function of time alone can equal a function of position alone, only if both are the same constant. Call it minus lambda. One reckless guess just shattered a partial differential equation into 2 ordinary differential equations. And those, we know how to solve. The spatial equation, with 0 temperature at both ends, is only satisfiable by sine waves that fit perfectly between the boundaries. 1 hump. 2 humps. 3 humps, and so on. The boundaries quantize the shapes. The time equation says each of those sine shapes simply decays exponentially. And here's the crucial detail. Look at the decay rates. The nth mode decays like e to the minus alpha, n pi over L, squared, t. That n squared means the 2 hump mode dies 4 times faster than the 1 hump mode. The 3 hump mode, 9 times faster. Sharp wiggles die fast. Smooth shapes linger. Watch. One problem remains. Our initial temperature bump isn't a sine wave. But this is where Fourier's great idea enters. Any reasonable initial profile can be written as a sum of these sine modes. Decompose the initial condition into its sine ingredients. Let each ingredient decay at its own rate. And add them back up. Already with just 5 modes, the sum lands almost exactly on our bump. That sum is the exact solution. The complete future of the rod. Watch what it predicts. The jagged details of the initial condition disappear almost immediately. the profile becomes smooth. And eventually, only the slowest single hump mode remains, fading gently to zero. Diffusion is a filter that erases detail. And now you know exactly why. Mode by mode. Separation of variables is beautiful. And fragile. It worked because our geometry was a simple rod, the equation was linear, and the boundary conditions were plain. Change any of those. An irregular shape. A temperature-dependent material. The nonlinear terms in Navier Stokes. And no closed-form formula exists. Not hard to find. Does not exist. So engineering takes the second path. If the PDE is a local rule about neighbors, then let a computer enforce that rule directly. Replace the continuous rod with a chain of points. Approximate the curvature at each point using exactly the neighbor comparison we built earlier. The value next door on each side, versus twice the value here. Then march forward in tiny time steps, updating every node by the local rule. Watch the dots track the exact Fourier solution, almost perfectly. That's the finite difference method. And this one idea, discretize the local rule, is the seat of all computational engineering. Refine it with volumes, and you get CFD, refine it with elements, and you get FEM. Every simulation you'll ever run is a PDE wearing a numerical costume. So, what is a partial differential equation? It's a local rule, written in the grammar of partial derivatives, that tells every point of a system how to respond to its neighbors. And from that one tiny sentence, the entire behavior of heat, waves, and flowing fluids emerges. Today you learn to read that grammar. To solve it exactly when nature is kind. And to discretize it when she isn't. If you want to see the numerical path built completely from scratch. No black boxes. Every line derived. The FEM from scratch and OpenFOAM from scratch series continue exactly where this video ends. The links are on screen. See you there.